Hello, my name is Eddine Benchikh from the University of Sherbrooke Mechanical Engineering Department, and today I'm going to present for you the numerical investigation of the capture efficiency of a domestic range hood. This work is governed by Sébastien Pensée and Hashimi Felwa from the University of Sherbrooke. This presentation is for the virtual conference of the ASME SHTC for the July 13 and 15, 2020. So first of all, the presentation will be, I'm starting the presentation with the context and state of the art, and then I'm going to present the numerical modeling, the geometrical parameters, the numerical methods and parameters, and then the validation, the different validations, and the results, and I will finish with the conclusions and perspectives. So the annihilation of different research found a strong correlation between the annihilation of particles emitted during the cooking activities and chronic obstructive pulmonary disease, lung cancers, and diabetes. So it's important to have efficient range hood in order to extract efficiently this pollutant in order to ensure the health of the kitchen occupants. Different research have been done during years in order to study the sensitivity of the range hood efficiency to different parameters as the cover shape, front overhang and rear gap distance, range hood height, range hood height, and flow separation at the leading edge, where the separation of the boundary layer can affect the capture efficiency of the range hood, positively or negatively. So most of the studies that have been done in the literature have been done using commercial software, and like CFX, Fluent, and StarCCM+, and they didn't take into account the range hood system, especially the motion of the fan and the motion of the different equipment of the range hood. So the objective of this current research is to develop an open source solver using the OpenFOAM in order to predict accurately the range hood capture efficiency, and we've taken into account the rotation motion of the fan inside the range hood. And then we want to provide guidelines to establish a common regulation for range hood performance. Concerning the geometrical parameters, we model a 3D scale full kitchen with the length of 2.5 meter and height of 2.5 meter, width of 3.5 meter. So the kitchen is equipped with 3 air inlets. In this case, we take into account only one burner on, where the CO2 as pollutant is introduced to the kitchen by this burner. And then this pollutant is extracted by the range hood and escaped the kitchen through an outlet pipe. So the range hood, we can see here in this figure, this is the different equipment of the range hood. We have the motor housing and the rotating ring and the blades, rotating fan and with 11 blades. So the diameter of the fan is 0.28 meters, and the rotation motion of the ring and the fan have been taken into account in these simulations. Concerning the numerical methods, we used the open source OpenFOAM 4.1, and we used a modified version of the Boolean-Boussinesq simple form, where we introduced a passive scalar transport and diffusion equations. We run 3D steady-state range simulations. For concerning the advection schema, we use the second order Gauss linear in order to have high accuracy, and use the turbulence model Omega SST in its low Reynolds approach. And concerning the boundary condition, we imposed a mass flow rate of this value at each air inlet of the kitchen with a turbulence intensity of 5%, and we imposed a mass flow rate for the CO2 at the burner surface of this value. And then concerning the temperature, the air have an ambient temperature of 293.15 Kelvin, and for the CO2 have a temperature of 400 Kelvin respectively. And for the initialization, we initialize it with an atmospheric pressure with 0 velocity and ambient temperature in all the kitchen. So concerning the approach, we use a passive scalar approach, which is a transport, which is an advective diffusive equations. So we have this equation is going to model how the CO2 is going to be transported by the main flow of the air. So this equation is divided in 3 parts. We have the temporal part, the advective term, and the diffusive term. The temporal part is equal to 0 because it's a steady state simulation. The advective term is going to model how this concentration, which is the CO2 concentration, is going to be advected by the main flow, and the diffusive term is going to model how this concentration is be diffused on the flow using the diffusive coefficient, the DC. So this passive scalar approach was used successfully for different configurations, as for the three-dimensional turbulent rectangular fidget by Venuta et al. And we have also in turbulent mixing in the ocean mixing layer by Bamidipati et al. And also in mixing dynamics in an uncovered buffet stirred tank by Ramirez Cruz et al. And also this approach has been validated successfully against the experimental results for CO2 plume of Xing et al. That I'm going to present in the after slides. Concerning the mesh, we have an unstructured mesh of 6 million cells elements in all the kitchen, with 1.4 million cells element only in the rotor region, where we need to model accurately the flow, the rotation motion of the fan, and the dynamic motion of the flow around the blade, because a good prediction of this flow going to ensure a good prediction of the extraction of the pollutant, and then a good prediction of the capture efficiency. We have 10 prismatic layers around the rotor blades, and we have a refinement in the range hoods, the stove regions, and the fan regions. And also we have a maximum white lice in the wall kitchen is lower than 0.9 in order to ensure the low Reynolds approach. So the developed open form servers that use it here to model the extraction of the CO2 by the range hood system has to predict accurately the three main phenomena occurring on the kitchen. So the three main phenomena occurring in the kitchen, they're occurring simultaneously. We have first of all the CO2 transport, where the CO2 is introduced to the kitchen through the burner, and then is then extracted through the range hood system. So we have to model accurately the CO2 transport. Secondly, we have to model accurately the heat transfer between the CO2, the introduced CO2 at 400 Kelvin, and the ambient air. And the third part, we have to model accurately the rotation motion of the fan. So this solver has to predict accurately each phenomenon separately. To do this, to validate our solver, we couldn't find a simple one experimental study that have the three phenomena occurring simultaneously. So in order to validate this solver, we validated each phenomena separately, and then when we'll be confident about the accuracy of the solver, we are going to apply this solver to the kitchen, and we are going to predict the extraction of the CO2. So first of all, we are going to start with the validation of the heat transfer. So use it here, the common reference that usually used is the Nielsen study for a differential heated cavity with a superimposed flow, where we have here the cavity and the ambient air is introduced through the left surface, and the different walls are adiabatic except the bottom wall where a constant heat is imposed. And then the air exits the cavity through the right surface. So here we used our developed solvers and we run the simulation, and what we can see here, this is the the distribution of the velocity in a vertical line, the distribution of the horizontal velocity in a vertical line. So we can see here we have an excellent agreement between the present solver in black dashed line and the experimental result of Nielsen results, with less than 1% of error. And we have also an improvement of a previous published numerical results of Liman et al. That you can see here in blue lines. For the heat that have been imposed in the bottom surface, we use the customized heat flow condition. We'll be using the lib-groovy boundary condition library of OpenFOAM. So this is the first phenomena, have been validated successfully against the experimental result. So going now to the second phenomena is the CO2 transport. So here we used the experimental result of Xing et al., where they studied the advection and the diffusion of the CO2 that have been introduced in an open space through an intake at mass flow rate of 10 at this mass flow rate, and then they studied the concentration of the CO2 downstream this inlet. So here we can see this is the distance from the intake and this is the normalization of the concentration of the CO2 by the concentration at the intake. So what we can see here, we have a good prediction of the maximum of the peak position, with some overestimation of the maximum value by 8%, and this overestimation could be to the instantness of the flow, as our simulation is steady simulation, and we have a large improvement compared to the former range simulation of Xinge all by using different turbulence models. So now this the second phenomena is validated successfully against the experimental results, and we have now the third validation. We have to validate the rotating motion of the fan. So we validated this rotation motion by studying experimentally in-house the fan that used it in the range hood, and we extracted the different performances curves here, the delta P and the rotation speed. So we have a very good, we predicted excellent, we have a good prediction of the performance curves with 0.8% of discrepancies compared to the experimental results. And this is going to be, as conclusion, it means that the multiple reference frame, the MRF approach that you used here to model the rotation motion of the fan, can be used confidently to model the fan motion of the range hood. Successfully, the three phenomena occurring in the kitchen, we applied the developed solver to the kitchen, and we imposed the CO2, the intake of the CO2 inside the kitchen, and we calculated the capture efficiency for different flow rates of the range hood, is varying between 100 CFM to 600 CFM, and the capture efficiency has been calculated as follows, where the C exhaust is the capture is the concentration of the CO2 at the exhaust with the outlet pipe. C chamber is the CO2 concentration inside the kitchen, and the C ambient is the CO2 concentration at the air inlet. So what we can see here, we have an increase of the capture efficiency by increasing the fan flow rate, and the increase from 100 CFM to 300 CFM will improve the capture efficiency by around 35%. And we are going after that, after 300 CFM, we are going to reach a constant regime where 100% of the capture efficiency is recorded. And in order to have a better idea about the flow inside the kitchen, we extracted the CO2 distribution between the stove and the range hood in the front view at the different flow rate between 100 CFM to 600 CFM. Where you can see here at 100 CFM that the flow is completely, CO2 is completely scattered and follows a no uniform distribution, but however, by increasing the flow rate, the uniformity of the CO2 is improved. Where at 600 CFM, we can see that the CO2 is extracted vertically with a conical shape near to the range hood. However, at 400 CFM, we can see a special capture regime where a left shift is observed, and this left shift is going to the side of the fan rotation direction. In the lateral view, where you can see here at 100 CFM, we have an important amount of the CO2 escape at the kitchen, but at 300 CFM and 600 CFM, the CO2 flows toward the bottom side of the range hood, and at 400 CFM, an arc shape is observed toward the kitchen, and at 600 CFM, the CO2 is less dispersive compared to the other flow rates. Concerning the temperature distribution, here this is the temperature distribution near to the range hood. You can see at 100 CFM, we have a uniform temperature distribution, but however, by increasing the flow rate, we have an increase. It will lead to a no homogeneous distribution, but however, we can see any specific temperature distribution pattern can be distinguishable by increasing or for the different flow rates. So at the end, as conclusions, we developed a new open form solver to predict the CO2 captures and have been validated carefully for the heat transfer, CO2 transport, and rotation motion. We have an improvement of the capture efficiency by 35% when the flow rate is increasing from 100 to 300 CFM, and we reach a constant regime at 330 CFM. At 100 CFM, the CO2 is extracted no uniformly. At higher flow rates, the CO2 follows a vertical patterns with a conical shape near to the range hood. The temperature feed is now inhomogeneous near to the range hood, and as perspectives, investigate the effect of the range hood shape and fine design and the capture efficiency. On the capture efficiency, we want to integrate the developer observer in optimization loop as Dakota, and then we want to compare the current results with a compressible solver coupled with the species equations. Thank you for your attention.